It's 11 o'clock, so I guess we can get started. So we are going to continue the data analysis part. So first, we are going to look at to conduct a comparison of the data with errors. And then we are also going to talk about identification of the outliers and the linear regression. So first is t-test. So suppose we have two samples that are analyzed under identical conditions. For example, we have the first sample, sample 1, which has mean, which is x1. So this should be x1 bar and x2 bar. I guess this should be a display arrow with its mean and the standard deviation from N1 replicates analysis. And we have another sample, sample 2, which has the mean of x2 bar, and the standard deviation is x2, and the sample size is n2. So usually we have the question, are they significantly different, or are the results are significantly different? So although we ask this question, but to be more specific, we are asking the question like, is the population mean of the first sample equals to the population mean of the second sample? Like we're asking if they are equal or if they are not equal. And to answer this question, we can use the method which is called t-test, or the full name is two-tailed t-test for independent means with equal variance. But in this class, we can only consider it as t-test, and we assume all the assumptions here are satisfied for our data. But I want to show that, and like in the future, in a graduate school, you may conduct some other type of t-test. They may be one-tailed, or the means are not independent, or the variance may be unequal. So at that time, we can find other methods. And the method here is like this. First, we can construct a range. We can see this is plus and minus. So basically, this is a range. And we can see if 0 is inside this range or outside this range. So basically, if 0 is inside this confidence interval, then there is no significant difference. And if 0 is outside the confidence interval, then we can see they have significant difference. And so here I want to just briefly talk about why we have this method. So basically, we are interested in if mu1 equals to mu2, or they are not equal. And then we can transform this question into another one. We can define a difference d, which equals to mu1 minus mu2. And if d equals to 0, which means they are equal. And if d does not equal to 0, then they do not equal. So we transform two variables into one variable. Let me just check. And from statistics, we know that if a sample follows a normal distribution, then its sample mean follows a t-distribution with some degree of freedom, some mean, and some variance. And another sample is the same. It follows a normal distribution, and its sample mean follows a t-distribution with some parameters shown here. And we're interested in the difference. So the difference of two t-distribution also follows a t-distribution with some parameters like the n, mu, and sigma here. And based on the distribution of this d, like here, we can construct a confidence interval like maybe here, like this is A, this is B. And between A and B, this has the 95% of the area. So if 0 is inside this area, we can say 0 equals to D or D equals to 0. And if 0 is outside this this range, then we can see D and 0 they do not equal. So finally, we can do some deviations, and we can have this result. So basically, when we have 95% confidence interval, which is a range of this A and B, and then we can say it should be automatically disappear. Nice. Still here. Okay, anyway, so if 0 is inside this 95% confidence interval, then there is no significant difference. And if 0 is outside this confidence interval, then there is significant difference. So basically, these two are equivalent. And then let's take more look at this formula. So basically, we have x1 bar minus x2 bar, which is similar to here. And we have a t here, and we have this s, which represents something like the standard deviation here. And we have some combinations of sample size. It represents the sample size or the degree of freedom here. So how to calculate these parameters? So for the S, it is the weighted average of S1 and S2. And the N is the total degree of freedom, and the N is here. So it's equals to N1 plus N2 minus 2. And we also have an alpha here. Alpha represents the significance level. And usually we just let alpha equals to 0.01. Yes.
So for that equation, it's 0, and then what does it say? Like,
so we can determine if 0 inside this range or outside this range. So for this one, do you guys have more questions?
Can you explain the 95% field of view again?
Yes. So if we want to find the 95%, we can use this T table. So as we mentioned, we have T, this is N, and this is alpha, or this is 0.05. So we have the T table here, and the degree of freedom refers to the N here, and 0.05 here. So we can find this value by using the T table. And here shows an example. So we have two measurements like of TCE concentration, and this is the structure of TCE, and this is not important. So based on the data, we can calculate the mean of each group and the standard deviation of each group. And then we want to determine if 0 is inside this range or outside this range. So first, we need to calculate this range. So in this equation, first we can say N. N is the degree of freedom, which equals to N1 plus N2 minus 2. So it equals to 18. And for the S, it is the weighted average of the two small a's. And here, because the sample size are the same, so we can just take the average of these two small a's, which is this value. And then for the T with N and alpha, as we mentioned, the N equals to 18, which is here. And the alpha is 0.01. And in this case, we can find it on the T table. So we have 0.05 here, and N equals to 18. So we can find the value, it is this one. And here we have everything ready, and we can just plug our value into this equation, and we can have this one. Just note that this is plus and minus. And after the calculation, we can get this range. So we can get this range. And we can see 0 is outside this range. So the conclusion is they are significantly different. And we usually add this note because the alpha may change, and in this comparison, the alpha equals to 0.05.
What is the P?
Oh, the P, they can understand the P is kind of like the probability that they make mistakes of this conclusion. Like, so basically we can say that the probability that they make mistake of the conclusion that they are significant difference is smaller than this probability. So the probability is relatively small. But in reality, the formal definition of P actually is more complicated. So
Yeah.
yeah. So any more questions? So I recommend you guys to do this calculation by yourself after class, and then you make it more familiar with it. So any more questions? Yes.
Where'd that N equation come from again? Did that come from the last slide?
This slide?
Okay, all right, yeah. Never mind. Yeah.
Okay.
Quick question there.
Yes.
Was the S standard deviation?
Which is?
The top one.
It's not.
No, the on the table. Yeah.
Yes, it
The
refers
standard.
to the standard deviation of
Of
these samples.
just the value, not the percent.
No, it is a value. Right. Okay. And then we are going to talk about the outliers. And as we show the example of outliers, actually I just prepared this in this slide, but we can see, suppose we have like the index, like the trails, like they just analyze the same thing for 100 times. And we can see we got the data like this, and we can see they are the same. But the only difference is that we have the red point here. Let's just say A, B, and C. So, do you guys think A is an outlier? How many of you think it is an outlier? All of you? Yes. So in this case, we can easily say, and we can easily reach an agreement that A is an outlier. But how about B? How many of you guys think B is an outlier? Some of you, and some of you does not think. Let's look at the third one. How many of you guys think it is an outlier? Yeah, we can say as the situation increase, like our agreements just decrease. So in this case, I want to show that for some of the situations like B and C, we may have some disagreements. So we need to find a method that is more objective. Like everyone can follow that method, and then we can reach an agreement. I would like to talk about the box plot method to identify the outlier. So let's just look at our situation. Suppose we got some measurements from our sample, and again we have x1, x2, blah blah, and x10. So we have a question: are there any potential outliers in the data set? Here I have a quote of potential. I will talk about why I mention this as potential here. But in this class, we can just ignore this potential here. We can just consider the outliers identified by box plot methods. They are outliers. So to identify the outliers, we need to construct a box plot. So this box plot has 5 elements. The first one, we need to figure out the maximum value in our data set. And then we need to figure out the minimum value in our data set. And this is relatively simple. And then we need to find the median of the whole data set, which is noted as Q2. And I guess you guys know how to calculate the median of a data set. We just reorder it and find the middle one. And then we split the data into 2 parts by using the median. So we calculate the median of the upper half, noted as Q3. And then we calculate the median of the lower half, and noted as Q1. So basically, we do not do so much calculation. We just need to reorder the data and then find maximum, minimum, Q1, Q2, and Q3. So by having all this ready, then we can calculate a value which is called interfrontal range, IQR. And the IQR refers to the range of this part. So basically, it refers to the length between Q3 and Q1. And because Q3 is always greater than Q1, so this range is always positive. And by having this IQR, then we can do more calculations. So first, we can calculate this upper fence, which is FU, like U refers to the upper. It's equals to Q3, which we already know, plus 1.5 times IQR. IQR, we have already calculated, so it is also a lower value. And then we can also calculate the lower fence. I can make it a little bit larger. We can also calculate this lower fence, which equals to Q1 minus 1.5 times the IQR. And again, Q1 is known and IQR is also known. So this lower fence can also be calculated. So in this case, everything can be calculated. And finally, we have this upper fence and lower fence range. In this range, we can do the same thing as a t-test. If our data belongs to this that does not inside this range, then Xi is considered as an outlier. So if we have some data here, because this is outside the range, then it is an outlier. Yes.
What does IQR stand for again?
Oh, it stands for the interfrontal range. Do I read it correctly? Interfrontal or interfrontal? Interfrontal. Yeah. So let's look at an example. Suppose we have the data here, and when we have the data, the first thing we need to do is to reorder it from small to large. And here I have already reordered the magnitude of the data. And based on the data, we can see first we want to find the minimum value, which is 20, and the maximum value, which is 56. And then we can find the median. For the median, I think this is here because it has even numbers. So we just take the average of the two middle ones. And for the upper half, we can find the median, which is this one. And for the, this is lower half. And for the upper half, we can find the median, which is this one. So we can find the maximum, minimum, Q1, Q2, and Q3. Yes.
If there had been like a single number that had come to then when you split it into upper and lower quartiles,
Each part will be even number. Right. Oh, yeah. If we have like, suppose we have 5 samples, and this is a median. So for the upper half and lower half, actually this is a little bit controversial because based on the Wikipedia, we have 2 methods. The first method is upper half and lower half. The second method is upper half and lower half. So we have 2 methods to do this split. And then we have 2 different Q1 and Q3 based on the 2 methods. So I would say both of these methods are acceptable. Yes, but this is a good question. I also made this question before. But in the quiz, I will make sure we only have 1 method. But if you find the two methods, or I didn't realize that, then let me know. So, okay. And then based on this Q1, Q2, and Q3, we can have this IQR, which equals to 8. And then we can calculate the upper fence and lower fence, which is Q1 plus 1.5 times this IQR, and the Q3, and Q1 minus this 1.5 times IQR. So we can have the upper fence and lower fence, and the range is this one. And we can, by having this range, we can see 20 is good, it's inside this range. But for the maximum value, it is outside this range. So in this case, 56 is an outlier. So for 1, we can, this is the end of this question. But in research or in practice, the further conclusion is that further statistical test is needed. So that's why I say this is a potential outlier, but we may need to use some statistical methods to confirm that it is an outlier. But in this class, we can just say this is an outlier. So any questions about this one?
So quick question, what tool did you use to confirm the outlier?
For the statistical.
Yeah.
Yeah, this is what I'm going to talk about in next slide.
Oh.
But do you guys have more questions about this slide? No? Yes.
So like on the quiz, like if we're like doing this whole like you could do either method of like including the loop or not.
Yes. Yes, but like I double checked with the data we already have done. But if you find we have two methods, you can let me know if I grade you as incorrect. Any more questions? Okay. Yes, here I put a star because I'm not going to ask you guys questions based on this one. But here I just want to show that we have some formal statistical methods for identification of outlier. And here example, which is from the guidance for data quality assessment, which is from US EPA. So this is a regulatory document. In other words, if we use the method recommended by this document, our conclusion will be, I would say, legally defensible because this is a government document. So in the section of 4.42, it talks about selection of statistical tests. And here is a table that shows the recommended statistical tests for the outliers. I'm not going to talk about them in details, but I just want to emphasize that for different sample size, we may choose different tests. Also, for the data, for most of the data, we will assume they follow the normal distribution. But for some of the tests, we don't have to meet this requirement. So and for some of the tests, they can identify multiple outliers. But for some of the tests, it can only detect one outlier. So if you guys are interested, you can download this document and read the details. Okay, so good. And this document, you can just search for the name and you can find this on the EPA website. The last one is about linear regression or calibration curve. So in the lab of this class, we are frequently using the calibration curve to get the concentration or any data from the instrument. And so here is a definition of calibration curve, and I'm not going to read it. But I just want to say that, so when we are preparing the calibration curve, we may prepare the solutions of different concentration, and these concentrations are known. We know how much chemicals are inside this solution. And then we send these samples to the instrument. And for the instruments, they can have some signals because basically this is a chemical information, but they want to check. But for the instruments, they can only detect the electrical information, and the electrical information or electronical information, it is kind of like if they are the signals of the instruments. So basically, we have sets of concentrations, and we also have the sets of the signals. So basically, we can construct the function or the relation between concentration and signal based on the concentration data that we know and based on the signal that we know. Then by having constructed this relation, one day we have a new sample here and the concentration is unknown. So in this case, we send this unknown sample to the instrument. Then the instrument will generate a new signal. And because we have already constructed the relation or the function between signal and concentration, then we can use this signal to back calculate the concentration. And in this way, we know the concentration of this unknown solution. So this is the idea of the calibration curve. And usually this relation are linear. So if this is signal and this is concentration, the relation are usually something like this. So we have lower signal, which we have low concentration. If we have high signal, we usually have a larger concentration. So this is something like the calibration curve. And I think in the lab, you guys will get more exposures to the calibration curve in future. So you guys maybe have more understandings on this one at the end of this class. So when we are constructing the relation between signal and concentration, as I mentioned, they are usually linear. So basically, we can use linear regression to construct this relation. So linear relation can be expressed as this one, which is too small. As this one, like yi equals to a plus xi. We should have a b here. I guess that is a typo. A plus b times xi plus eta. And in this one, this is pretty like the equation of a straight line. And for the linear regression, we have this, which we are familiar, like x and y. They have different names. Actually, I find this table from a metrical book. So x and y, they have many names and they have many pairs. But in practice, people can use them interchangeably. So sometimes they may call y as explained variable, but they call x as regressor. So that is okay. And we can use these names interchangeably. A and B here are two parameters that to construct the line. And eta here is the arrow term. I can talk more about eta in the next slide. So eta is the arrow term. And usually eta follows a normal distribution. So if this is a normal distribution and the mean equals to 0. So basically it tells us that because the mean equals to 0, so if we take many samples and take the average, then the influence of eta will be small. It will be smaller because its mean is 0. Some of the eta can be cancelled out. And to be most, like if we visualize eta, it will be something like here. Eta refers to the difference between the real points and the points on the regression line. So this distance refers to eta, right? And here and here. And this and the length of this eta follows a normal distribution. And we can see it follows the same normal distribution. So we can see an example. And so in practice, we will have an array of x values. And we also will have an array of the corresponding y values. And we can do this in Excel. So this is x and this is y. And then we can construct the linear regression by using Excel. So if you guys are not familiar with how to use Excel to construct the linear regression, you guys can search this online and just several clicks, and then we can get this plot. And Excel will also provide this regression equation. For example, like this one, the regression equation is this. So far, I think most of the people can do this part by using Excel. But we have some more questions because we have already talked about the errors. So the question is, how about the uncertainty or the errors of A and B? Like here and here. And also, if they have a new data, new x here, and just say let's x new equals to x0. And we know if we have a new x data, we can just plug this x into this regression line. And then we can get the new y value, let's say this is x0, this is y0. But we are also interested in what's the uncertainty of this y0. And this does not tell us. So in this course, we need to find the uncertainty of this stuff. And to answer this question, also for this example, do you guys have any questions?
I have a
Yes.
question, but it's on the last page. Could you back it up?
Yes.
Just the example you gave us about the concentration and signal, you just plot like a Capron curve. I just want to make sure, are you sure the X should be the signal and Y should be the concentration?
Oh yeah, that's a good question. So in some of the practice, like or some of the device, they will use the C as concentration, and they will use the signal. They will use the concentration as x-axis, and they will use the signal as the y-axis. But as I mentioned here, so basically, when we have the new sample, the new things is the signal. So we are going to use the signal to predict the concentration. So generally, the signal is the dependent is the independent variable because this is new one, and then the concentration depends on that signal. So in this case, we can also have this linear relation. But when we got the new signal here, we just use this to do this direction. And for the example I mentioned before, we do this part. So basically they're the same. But in practice, we may have different ways to express this relation. That's a good question. And so to answer these questions, we have something like this. And I guess this is a little bit overwhelming because it has so many equations. But if we just split them apart, I think this will be more straightforward. So basically, we are interested in the uncertainty of A and B. So so we're interested in the variance or the standard deviation of B and the variance or standard deviation of A. In addition, if we have a new data here, we want a Y, like the uncertainty of Y. So in this case, we have two results. But in this course, we will be focusing on this one. So predicted response, which is Y0 hat. So the hat in statistics generally means that it is the estimation of that value. The difference between mean response and predicted response is that, so there should be Y bar hat. So this is Y bar hat and this is Y. So for example, like this is our calibration curve. Let's just say this is a concentration and this is a signal. So I have a new sample. Sometimes we only measure it once. If we measure it once, we will have a new signal, and then we can use it to estimate the concentration. And this corresponding to this situation because we only do it once. But for some other situations, we still have this sample, but we measure it 10 times or n times. If we measure it n times, then we have many signals here. And then it will have another concentration. In this case, it means that if we have many signals here, what is the average predicted or estimated concentration in this situation? But usually we do not use this method in our lab or in this class. So we will only focus on this one. And we can see the difference is that we have a 1 here. And so basically, this one is larger than this one. And this is making sense. And this makes sense because if we do it several times, the uncertainty will be decreased. So basically, we will be focused on this one. And here, I just show some of the steps that we can do the calculation. And the colors indicate different steps. So let's just look at this one by one, step by step. So first, step 1, which is blue. So basically, based on the data, we can calculate X bar. So they should be X bar and Y bar. And they can be calculated by using our X data and using our Y data. And then we can calculate the sum of squares, which is SX, X, SXX, and SYY, which equals to the XI minus X bar. So in these two equations, Xi is known, and X bar and Y bar, they are also known. So SXX and SYY, they can also be calculated. It may take some time, but we can calculate this value. So basically, we start here from here, and then from here. And then the next step is to calculate the sum of both products. Again, X bar, Y bar, we know, and XI, YI, we also know. So we just do this for I times, for n times, and then we just take the sum of them, and we can obtain X, S, X, Y. So we have all of this here, and the next step is to estimate A and B. So in this case, B equals to SXY over SXX, and these two values are known, so we can calculate the B value. Again, I put a hat here, it just shows this is an estimated value. And by having B, and we know Y bar, we know X bar, and we know B here, so we can use this to calculate A. So A value can also be calculated. And the next step is to calculate this sigma hat square. So basically, sigma hat square equals to the big S square here. As we mentioned before, we assume eta or the arrow follows a normal distribution with a variance, and this variance is unknown. And we can use this equation to estimate the variance here. So to calculate this, we want to know the value of eta. So basically, we just have the eta 1, eta 2, eta 3, and the x square, and sum them up and divide it by n minus 2. So to calculate eta, we will use this equation. So in this case, we know xi and yi, which is our data. A and B have also been calculated. So eta 1, eta 2, eta 3, they can also be calculated. So we can use this equation to calculate each eta. So eta I is known and n is also known, and we can use this equation to calculate the sigma. So by knowing the sigma, this one is known. Then the next step, we are going to, so basically from here, we have already constructed our linear relation. But the next one is to calculate the uncertainty of the parameters. So the variance of B or B hat can be calculated by this equation. And we already know sigma square. And we already know SXX. Then we can calculate the variance of B. And again, the standard deviation is STD of B just equals to the square root of the variance of B. And for the variance of A, we already know Xi, and we already know sigma square. We already know N, and we already know SXX. So the variance of A can also be calculated. Again, it may take some time, but we can do the calculation. Here I also show this one, but we are not going to do this calculation here. But here I just want to show that for the linear regression, we can see that the intercept and the slope, they are correlated. So that's a point. But we are not care, we do not care about the correlation here. So we have this done. This is good. Now let's look at if we have a new data, which is x0, and we want to calculate the new y. So let's just ignore this one. If I take a look at this one. So for the new y, this is easy. We just plug the new x0, plug this into the linear relation. We already know b and a, then we can know y0. And for the uncertainty of y, this can be calculated by this one. And again, this is x bar. So x bar is known, x0 is known here, and SXX is known, N is known, sigma is known. So everything is known, and we can calculate this one. So this looks a little bit complicated, but finally we can get this done by using this path. And I think this is a little bit abstract, but we can just transform this path into an Excel sheet. I think this will make more sense. So again, I use the colors to indicate the steps. Let me just make it a little bit large. So again, we start with our data. We can calculate X bar and Y bar. Because in the Excel, we cannot input the complex mathematical notations. So I just use this to express. And then we calculate SXX, SYY, and SXY. Again, because we have XI, like we have a list array of the data, and we take the sum of them. And then we plug them, like we can calculate the y hat and y minus y hat. So anyway, finally, we can calculate this eta square. And but by having the eta square, we can estimate our A and B. So in this case, I use the Excel to do the calculation. This is the result of my A and B. And this is the result from the Excel, like the auto-generated A and B. We can see that they are equal, which means this calculation is correct. And again, we can also follow the path. And finally, we can get this y hat and the variance of y bar hat, or of y hat. I think this should be y hat. Yeah, so anyway, we can use this Excel to do the calculation. So we don't have to handwrite to do the calculation by ourselves. And I would recommend that you guys may reconstruct this Excel sheet by yourself. And then you can compare if the data equals to the data here. And you can see you do it correct. So, any more questions about this? Yes.
Can you go back to the previous slide? The first, the equation on the top and on the right, like, in the script. What are the dots? Or like Y dot?
Oh, this should be expanded by bar.
Oh,
Yeah, I think, let me just double check. Yeah, in this view, they can see this is correct. But when I just play this slide, it's, yeah. But when I print this into PDF, I will double check if it is correct. Just make sure. So any more other questions? Yes.
If we were asked to do this, something like this, in like a lab report, would we be able to use MATLAB? The Excel software?
You may use MATLAB, but I just go through this process because I want you guys to get familiar with how exactly it is calculated. So if we are using, I don't know, like for the others, of course, we are using the software to do the calculation. But if they know the mathematics behind, sometimes when it gets the weird results, we may figure out why this comes. Yes.
And just a quick note, that A and B, the pink one that we calculated, those are the A hat and B hat.
Yes, yes. Yes, they like to be more. But we can consider it as an A and B in the regression equation. So any more questions? And we have 3 minutes. And here, just the assumptions of the linear regression, because I didn't talk about this in the class. So basically, I just want to just briefly talk about this. And again, I'm not going to ask questions about the assumptions. And so basically, the data should be linear. And if the data is in a curve, then we should not use linear regression. Second, the homogeneity, I don't know how to read it, but it means that if we have data here and if we do the linear regression, we can see that when the data gets larger, then the eta or the data are more scattered from the regression line. So in this case, we should not use linear regression. We need to make sure that the data are just uniformly or something like that distributed along the regression line. And the second one is normality. So basically, it means the eta should follow a normal distribution. If the eta does not follow a normal distribution, we should not use linear regression. And the next one is independence. And this shows the autocorrelation of the data. So basically, we need to make sure our data are independent trails. So this is the autocorrelation function. I will talk about this in lecture 7. And we can see this pattern is pretty similar for the example here. And this pattern represents the data like here. We can see this in the cosine line. So anyway, I will talk about this in lecture 7. And the last one is that we need to make sure our x, because for the multiple linear regression, we have like y equals to beta 0 plus beta 1, beta 2. So we have different x's. And we need to make sure the axes themselves, they should be independent or they should be uncorrelated. And I think that's the end of this lecture. But here I only have 2 notes about the homework assignments because we have students who have some questions about them. I just briefly go through them. You may have a question. If I'm doing the homework, I need to choose the balance or the pipette by myself. And here I just want to say, we use the one with capacity that is just greater than what you need. The next one, we may also have a question, what's the difference between if I use one pipette to deliver it twice, or I use a big pipette to deliver it once? And here I just show an example. You guys can take a look. But finally, the result is that if we use if we deliver the volume of the solution twice, the error will not get doubled. The increasing factor is square root of 2. So you guys can take a look at this. It's a little bit counterintuitive. So need to be cautioned about this. And so another one is some of you may not take 310. So in this case, we are going to calculate the total solids. The total solids equals to the mass after 103 over the volume of our sample. And that's it for today. Final notes, but you guys. So for the quiz 2, the last 3 questions, they are related. And because the ELMs, they may just shuffle the order of the question. I just want to make sure for the first question, we are going to have this calibration curve. And for the second question, this is based on the first question. We can see we have the second sample, blah, blah, blah. And for the third question, we have the third sample, blah, blah, blah. So when you guys are doing a quiz, you may just go through the questions and make sure they are in the correct order. And for the pictures, for the collaboration pictures, the best way is to take the pipe out and then take the close-up view of the pipe, something like this. So we can clearly see the surface of the pipe. And that's it.